Okay, hello, Aman. Good morning.
Good morning.
Okay, so if you have any question at any time, feel free to unmute yourself, okay?
Okay.
Oh, wait. Okay, so let's start our lecture today.
How's your Thanksgiving?
Yeah, every vacation must be. Okay, so as a reminder to you, on the next lecture on Friday, you will have our second lab. Our second lab will be in this room. Okay, so don't forget this. So I will not be here on Friday. Omid, your TA will be your instructor or your TA during this lab. We have on the next week our midterm. Our midterm will be on Friday, October 22. Okay, the exam will be around 45 minutes. It will be very easy direct exam. Don't worry about this. Our final exam will be on December 14 at 8:30 p.m. And the location of the exam will be in the art building room 382, as I remember. Yeah. So December 14. December 14. This will be our final exam. Will be the end of our journey with this course. Okay. Let's return to our topic. In automatic repeat request technique, we know that this protocol enables the receiver to communicate with the sender and to receive at the end our packets in a correct way. We discussed the stop and wait, go back in, selective repeat, and today we will discuss the hybrid automatic repeat request. Actually, we want to enable the receiver to detect and correct the errors in the received data. So one of the techniques, if we have errors in the packet, one method, the receiver can request from the sender, please resend this packet in direct way. Another way, no. We don't want to waste the resources of our channel in retransmitting the process. So we want to enable the receiver to be able to correct the errors in the packet. How can this be done? Through adding redundant bits, additional bits over the transmitted packets. Okay, so in hybrid automatic repeat request, this is the basic idea of this technique. Adding additional bits to the transmitted packets. This will enable the receiver to detect if we have errors and may enable the receiver to correct these errors. At first, during the start of our transmission, no errors. So in the transmitter, we will add few number of additional bits. So the number of extra bits of the number of overhead will be very small, as long as we don't have any errors in the channel. But when we detect that we have errors or noise in the channel, so the hybrid automatic read request must increase the number of additional bits in the process of retransmitting. So at first, for example, we want to transmit this bucket, so we will add only 3 overhead bits or additional bits. These 3 bits will enable the receiver to detect if we have errors or not. If the receiver detects that, oh, we have errors, and the receiver failed to correct these errors, so the receiver will request from the sender, please resend back to me the buckets that have errors. So the transmitter will retransmit this bucket, but with increasing the number of additional bits. Okay, so this will help us to save our resources. At first, we have no errors, so the overhead size will be very small. Okay, but if we discover that the channel is noisy, we have errors in the channel. Oh, so we must increase the overhead size or overhead length. Okay, this is better, as in some techniques, the overhead length is fixed. Okay, so using fixed overhead length is inefficient, as we are wasting the channel resources. At some times, the channel is not noisy. There are no errors in the channels. So we don't need this large overhead, okay, all the time. So in this technique, this is better. We optimize the resources in the channel through optimizing the size or the length of the overhead. No errors, small overhead. Large errors, or we have many errors, large overhead. Okay, so this is the hybrid automatic repeat request. So now the question. We are dealing now with bucket, the bits, the data bits, and overhead bits. We want to know how we can determine the size of the bucket. This is a question, as based on the size of the bucket, this will have significant effect on the data rate, on the retransmitted bits, on the quality of the transmission. So the bucket sizing is one of the major parameters that can affect the transmission of your data. So suppose that we have a bucket, we have bits, P bits, and we want to transmit these B bits over M lengths. We have M lengths, and we want to transmit these M bits over these bits. And we have, for sure, we will divide these B bits over buckets, and each bucket contains K bits of data and H bits of overhead. So we will divide, in order to determine the number of buckets, we will divide the number of bits of data bits over the number of K bits of data in the bucket. Okay.
H, like the overhead, is that your error detection bits?
Here?
No, like
H
bits of overhead. Like what is
yeah,
that?
each overhead, each are the overhead bits that will be used at the receiver to detect and may correct the errors. Okay, so what is the use or purpose of the overhead? Overhead is used to enable the receiver to detect that we have errors, and may help the receiver to correct these errors. But this is not 100%. Okay, so this is the advantage of the overhead. But think again, these overhead bits are consuming our resources. So we want to minimize it as much as we can. So remember again, it is a trade-off relation. If we have large overhead, we will be enabled to detect more errors and may correct more errors. Small overhead will enable us to detect small errors and correct small errors. So the length of overhead will determine how many errors you can detect or may correct. Okay, so for sure it's better to have large overhead. This large overhead length will enable the receiver to detect many errors and correct many errors. But again, you are wasting the channel. For example, if we have B bits to transmit, and we add B bits as overhead, so I double the length of the data. In order to transmit B bits, I want to transmit 2 B bits. This is not logic. We are wasting our data rate. So the utilities of that channel will be inefficient in utilization. Okay, so again, everything in engineering is a trade-off relation. For sure, the best thing, the optimal thing that we need, the cost of this optimal will be very high. So as engineer, you are required to do this trade-off relation to minimize the overhead length bits as much as you can, but at the same time, you guarantee that the receiver will be able to detect the errors and the buckets. Okay, this is clear to you till now. So now we have B bits. We want to divide these bits into n buckets to be transmitted. Each bucket has k bits of data, and each bits of overhead. So in order to determine the number of buckets, what should I do? How can I determine the number of buckets that I will use?
Number of bits you need to send divided by the number of bits per time.
Yeah, so the number of packets will be equal B, the number of bits that I will send, divided by K, the number of data bits per packet. This is, we have n packets. Okay, so the transmission data per packet will equal the number of bits per packet, which will equal K plus each divided by the data rate. This will be the transmission time delay per packet, per one packet. The number of bits of packet, we have K data bits plus each overhead bits divided by the data rate. You have a question?
No.
Oh, okay. So in order to calculate the total delay to transmit these B bits over the M length, the total delay can be calculated using this equation. We have, this is the transmission delay of one packet, and we will multiply it with n number of packets. So this will be the transmissions delay for all packets plus m minus 1 multiplied by k plus h divided by r. This is called bibling delay. Bibling delay is the process time at each link. So we will transmit our bits over n link. At each link, there will be a processing, something like routing to process where these packets should be go and what is the source of these packets. Okay, so this process we can call it pipeline delay, and we have propagation delay multiplied by m, where m is the number of links. We have a very useful note here. If the number of bits is small, okay, this will reduce the pipe link delay, the processing time at each link, but this will increase the possibility of packet loss, because if the data is small, we will use small overhead. Okay, so this will increase the possibility of packet loss. This will increase the possibility that the receiver may not be able to detect the errors in the channel. If K increases, the pipeline delay will increase, but this will reduce the possibility of packet loss, reduce the possibility that the receiver may be not able to detect the errors. As at the end, we want the number of data bits to be larger than the number of overhead bits. This is logic. We can't transmit overhead bits larger than the number of bits that we want to transmit. Okay, so small k, small data bits, means that we will have small overhead bits. This will reduce the delay, okay, but will increase the possibility of packet loss, increase the possibility that the receiver may be not able to detect the errors in the channel, okay? On the other side, larger k means that we will need to larger overhead, and this will increase the delay, but reduce the possibility of packet loss. So now the problem is, how can we determine the optimal key, the optimal number of bits that we can use? Can anyone help me to solve this problem? So we have a relation. This is the total delay time to transmit our bits over our communication channel. And from this relation, we want to obtain the optimal key. And one hint to you, we can neglect the propagation delay at each link. So from this equation, if I want to know the optimal K, what should I do? Simply math problem.
You want to differentiate it in terms of K and then find the point?
Okay, after differentiate, after taking the first derivative, what should I do?
So equal 0 and so on.
Okay, this is the very simple solution to obtain the optimal value. We call this method in communications engineering minimum mean square error. What should we do? We want to determine the optimal K, and the K is part of this equation. So we will take the first derivative with respect to K. And after that, so we will take the first derivative of P with respect to K. And after taking the first derivative, we will make this first derivative equal to 0. So we can solve this equation for K. So after taking the first derivative of this equation and neglect the value of propagation delay, we can obtain the optimal K to be equal this value. Okay, so this is one of the important parameters that we must know how to calculate. Okay, as you can see, based on the number of bits, data bits in each bucket, this will have significant effect on the total delay of the transmission of the packets, will have significant effect on the possibility of packet loss, will have significant effect on the size of overhead. So the first thing you must know in order to transmit your packet to determine how many bits that data bits should be included in each packet. Okay, this is clear to you till now? Okay, now we finished lecture 7 and let's go through lecture 8, and this is a very simple topic here. I'm sure that most of the information included in this lecture, I think you have a good experience about it before. So now we know that we have data, okay? And we must add additional bits. These additional bits or extra bits we can call overhead. What is the function of this overhead? Okay. So how can we use this overhead to detect errors? This will be the main topic of this lecture. Okay. So we have two types of errors: isolated errors, which are bit errors that don't affect other bits. So in our stream, we may have one error in this bit, but this error may not affect the transmission of the other bits. So we can call it as isolated errors or burst errors. So we have a cluster of bits in which a number of errors can occur. In practice, to make you able to see the effect of noise on the transmitted errors, this is a practical example. 1 microsecond of impulse noise or fading in the channel can cause 2 bits errors when the data rate is 1 megabit per second. So for each 1 megabit per second, we will have 2 bit errors. If we have only 1 microsecond of fading or noise, okay? And the number of errors will increase as the number of the transmitted bit will increase for sure. If we transmit 100 megabit per second, the number of error bits will increase to be 101 bits. You can see this is the effect of only 1 microsecond of noise. So we must protect our data against this noise. We must enable the receiver to be able to detect these errors. So as you can see, all of these demonstrate the importance of using overhead. I know overhead bits are wasting our channel resources, but they are still important in our transmission. Okay, so receiver must be aware of that an error occurred in a frame, and we need to have an error detection mechanism. Receiver at the end must receive correct frame. So what should we do? We can add redundant bits to correct errors, okay? Or the receiver can ask the transmitter to retransmit the packet again. In practice, both techniques are practical and are used in the industry. So the receiver can, if the receiver detects that we have errors, send request to the sender, please resend it again. Or we can enable the receiver to correct these errors through using some error correction mechanism. Okay. The first simple error detection mechanism is the single parity check. And during your assignment, I think you will become more familiar with the parity checks. And I was very pleased as most of you got the full mark in this assignment. So this is good. Okay. So I want from you, anyone from you, to explain to me what is the basic idea of the single vertex check. Make it as a revision to you and enhance your communication skills. I remember in our first lecture, one of you told me that I joined this course to improve my communication skills. Yeah? Okay, so improve your communication skills. Can you explain the single vertex check to your friends? Explain the single vertex check. Yeah.
There's an even amount of ones in a packet.
Can you come here? Yeah.
Yes.
You are now our instructor. Yeah. So
Right.
explain it. Yeah. If you need. Okay.
Right. So a single parity check. It's a pretty simple concept. If there is an even amount of ones in a packet, you add a 0 to the end. If there is an odd number of ones in a packet, put a 1 at the end so that there is always an even amount of ones in the packet. When the receiver gets the packet with a parity check at the end, or with a parity protocol, they check, okay, is there a 1 at the end? Yes. Is there an even number of ones in the packet? If yes, then you remove the 1 at the end. You know that you're supposed to have an odd number of ones. Yeah, right?
Anyone has
Any questions so far?
questions?
Oh, it seems pretty straightforward.
Pretty straightforward?
Yeah.
Cool.
Perfect. Yeah. You have excellent communication skills. You have excellent communication skills. Yeah. So this is the basic idea of the single vertex check. So how many errors can the single vertex check detect?
Every odd, I guess, like 1, 3, 5.
Yeah.
7.
Every year. But so the single vertex check is efficient technique in terms of the size of overhead. We only need 1 bit single vertex check bits. So the size of the overhead is very small. So that's good, efficient in terms of the channel resources. But in terms of error detection, do you think that error detection is efficient technique or not?
No.
No, not efficient technique. So another modification over the single vertex check is to use 2-dimensional vertex check. Anyone here want to improve his communication skills and explain to us the 2-dimensional vertex check? It's good experience. Was it a good experience for you?
Sure.
Yeah.
Say yes.
Okay. At first, do you have any previous background about 2 vertex? No. Okay. So the idea of the 2-dimensional parity is the same as the single vertex check. We will divide our transmitted bits into a matrix. We have columns and rows. And we will do the same process of the single vertex check on each row and each column. So for example, we have here 35 bits we want to transmit. In single vertex check, we will count the number of ones. If the number of ones is even, we will add 0. If the number of ones is odd, we will add 1. So in single vertex check, we will add 1 additional bits for the 35 bits. Is this clear to you? Here, no. In 2-dimensional vertex check, we will divide our 35. 1, 2, 3, 4, 5. Yeah, okay. 35 bits into a matrix. So we have in each row 7 bits, and we divide them to 5 rows. So we have 7 columns, 5 rows. Okay, and at each row we will do the same process. Here, the number of ones is even or odd.
Odd.
So we will add 1. The number of ones here, even or odd. So we'll add 0. Here, even, so we'll add 0. Here, even, so we'll add 0. Here, odd, so add 1. Here, do the same process at each core. And transmit this matrix to the receiver. As you can see, for the 35 bits, we will need to add 13 bits as overhead. It is very large overhead to transmit 35 bits. I want to add 13 bits overhead. So it is not efficient in terms of the overhead size. But this method can enable us to detect and correct errors. How can? For example, if this bit is changed, we have error in this bit, and this bit become 1. Okay? This bit become 1. Okay, so when at the destination or at the receiver, we will check the number of ones in each row and each column as we did in the transmitter. So here, this is 1. Okay, so what is the number of ones in this row? Here. 1, 2, 3, 4, 5. So it's odd number. Okay, so but we have here, so we must add 1 as parity check. But the result that we have is 0. So there is an error in this row. Okay, here in this row, in this column, sorry. How many ones in this column? 2. So we must have 0, but we have already 1. So we have an error in this column. So we have an error in this row. We have an error in this column. The intersection is in this bit. So the error is here. So we must invert or flip these bits from 0 to 1. This is the way used in the 2-dimensional parity check to correct the errors, as you can see. But as you can see, in order to enable the receiver to correct errors, we must have large size or large length of overhead. So this is a trade-off relation, as I told you. Large overhead bits will enable you to do many things. Detection, correction, if you want. Small overhead will limit you in the number of detected errors or corrected errors, as you can see. So in the single parity check, we add only 1 bit as overhead. In 2-dimensional parity check, we will need to add 13 bits as overhead. From this example, you can see the difference. Small overhead, large overhead. Not efficient in error detection. We can consider it efficient in error detection. The third technique is cyclic redundancy check. Do you know anything about CRC before? Okay, so cyclic redundancy check is a technique that enables the transmitter, the receiver to detect that we have errors. The basic idea of this technique is as follows. We have bits to transmit, and we have generator key. So these are our bits. This our generator key. The transmitter and the receiver have the same generator key. Okay, so I am the transmitter. Okay, and Daniel will be the receiver. So at first we will agree this will be our shared key. Okay, so our shared key will be 1101. Okay, Daniel. Okay, Mahmoud. And we have our bits. What should I do? We need to add overhead, or we need to add redundant bits. How can we calculate these redundant bits? As follows. We will at first let's take this example first and then actually I like to explain mathematical methods using examples, not text. So we have 1 0 0 1 0 0. This is our data. 1 0 0 1 0 0. This is our data to transmit. Okay, and our generator key is 1101. 1101. This is our key. Known and transmitter and receiver. Okay. At first, what is the length of the key? 4 bits. So this is the first step. We will add k minus 1 zeros to the date. So I will add 1, 2, 3 to the date. So the first step, you must look at your key and determine the size of your key. 4, so I will add 3 zeros. This is the first step. The second step is to make binary division process. Can you do binary division process? Can you do it? Help me. You want to do binary division process. What should I do?
Sorry, binary division?
Yeah. Anyone can help me?
Taking overhead and divided by the key, or what are we dividing?
So what should I do now?
Are we dividing the whole byte?
Yeah, let's do the process. Okay, so in the binary, in the simplest way to make the binary division process, to see the length of your data and compare it the length of the divider. The length of data is larger than the length of divider. So it will be here 1 and multiply 1 by this data. So we have 1 0 1 1. After that, make binary subtract. Okay, so 1 minus 1 0. 0 minus 0 0. 0 minus 1 1. Okay, and we neglect the last bit and take additional bit from here. Okay, the size of our data is equal to the size of the divider. So we will add 1 and multiply 1 by our divider. So we have 1 0 1 1. 0 minus 1 is 1. 0 minus 0 is 0. 0 minus 1 is 1. Neglect the last bit and we are here. Yeah. Add additional bit here, 0. The size of our data is equal to the size of our divider. So we'll add, so here 1 and multiply 1 by with multiply 1 with the divider, so we'll have 1, 0, 1, 1. 0 minus 1 is 1. 1 minus 0 is 1. 0 minus 1, 1. Neglect the last bit and get additional bit from here 0. The size of the data is equal to the size of the divider. Okay.
Why is, you just said 0 minus 1 is 1.
0 minus 1 is 1, yeah.
Should that be -1?
We are in binary.
So we don't even care.
Yeah. So use this as main rule to you. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 1 is 1. Okay?
Okay.
As we will borrow 1 from the next, but here in this process, this will be the basic simple idea. Okay.
If you're gonna do this by hand, like wouldn't it be quicker to just go to decimal and do it that way?
You want to do it using calculator, for example?
No, just convert it to decimal, like. I don't know, if we're doing it like a long division by hand anyways, I feel like it would be.
Actually, I'm not sure if you do it as convert it to decimal and make the division process, we will have the same result or not. Okay, let's see. I will continue. Okay, so 0, 1, 1, 1. We will compare it to this. This will be 1 and multiply 1, 0, 1, 1. 0 minus 1, 1, 1, 0, and neglect this. Yes, neglect this 1, and we will add here 0. So the size of our data now is 0. That's no need. So we have 0, 1, 1, here 0. So the size of our data now is less than the length of the divider. So we will have here 0 and multiply 0 by this. So we will have 0, 0, 0, 0. And then make division process, subtract process 0, 1, 1. And 0, we'll get the last one. Compare this by this. This is have equal lengths, so we have 1 multiply 1, 0, 1, 1. What we will have is 1, 0, 0, and neglect the last one. So this is called the remainder of our division process. What will we do is to take this remainder, okay, and add this remainder to our transmitted bits. So now our data is 0, 0, 1, 0, 0, 1, okay, and we will add 3 bits, the remainder bits to our data. And this will be the overhead, and this will be your bits, and we will transmit this back. So this will be K, and this will be H. Okay, is this clear to you? Okay, so now we are able to calculate the overhead bits. And after that, we add these overhead bits to our data and transmit them to the receiver. So again, at first, we will see our data and we will see our key. Based on the length of our key, we will add K minus 1 bits zeros to our data. Okay, this is the first step. And after that, make binary deviation process as usual between our data with the added zeros bits, and At the end of this binary deviation, we will have a reminder. We will take this reminder and add it to the original bits, and this will be our transmitted data. At the receiver, this is the data received at the receiver. Okay? And the receiver, Daniel, you know the key, yeah?
Yeah.
We agreed.
Yes.
Yes, okay. So Daniel now received the data bits and the overhead bits, and Daniel knows the key. So Daniel will make binary deviation process again between the transmitted data and our key. Okay, if the reminder of this process is zeros, this means that we don't have any errors and the data is received in a correct way. If the reminder here is not zeros, this means that we have errors and we must request from the transmitter to retransmit our data. So you understand the basic idea of CRC. So we no share the key, the transmitter and the receiver, no share the key, okay? And based, again, this is a revision. At the sender, I know the shared key. I will see the length of this key. For example, 4 bits. So I will add 3 zeros to the transmitted bits and make binary deviation between the bits with the added 0 bits and our key. The result of this the binary deviation process, we will have a reminder. This reminder will be our overhead. We will add this overhead to the transmitted bits and transmit them to the receiver. As the receiver knows the same key that the transmitter used. So the transmitter, the receiver will make another binary deviation process between the received data and the known key. If the result of this binary deviation process is 0, this means that no errors in the packets. If, as you can see this in this example, we don't have any errors. In example 2, we will have the result as the receiver will not equal to 0. This means that we have errors in the transmitted data, so the receiver, the transmitter must retransmit this data. The advantage of this technique is that with small number of additional bits, the receiver can detect if we have errors or not. Okay, so as you can see in single byte check, if we have 2 errors, the receiver will not be able to detect if we have errors or not. But here, using this small number of overhead bits, as you can see, the receiver is able to detect if we have errors or not. CRC is clear to you? The way that we can do it is clear to you?
Can it detect like any amount of errors?
Yeah, as at the end, here it is not the responsibility of CRC to detect how many errors that we have. Okay, if we have 1 error, we have error in the packet. Okay, and we must fix this error. And if the receiver is unable to fix this error, it will request from the transmitter to resend this packet again. So here, at the end of this process, the receiver will be able to detect if we have errors or not, no matter how many errors that we have. Okay? It's okay with you? Everything's okay? Clear? Okay. So we are done today. If you have any question, feel free to ask me at any time. And remember, on Friday, our next lecture, Omid will be with you to teach to you your second lab.
Okay.
Do you know if there's someone in this classroom after? Like, is there another class right now?
I don't know, and I don't think. I sometimes yeah we left from here after 9 and there was no one come to the table. So if you want to stay here, you can.
Let's hate it. I guess we could move on there and stay.
Okay, Thomas, everything is okay to you? Clear to you?
Yeah, so.
Okay, thank you so much
It takes.
and have a nice day. Bye.